Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to look at using the general power formula for finding integrals. When you were doing differential calculus and finding derivatives of functions, there was a rule for every type of function you encountered. Now when we're doing integral calculus, it gets trickier. We can't look at an integral and know exactly what rule we're going to use. There's all these methods or techniques, and you won't necessarily know which one you're supposed to use. So I'm going to be looking at all of the different patterns and what to look for so that you can recognize the pattern you should be using to do the integral. So we've done the general power rule before, the integral of u to the n du, and we know that it's equal to 1 over n plus 1 times u to the n plus 1. And if you're doing indefinite integration, include your constant of integration. The requirement here, very important requirement, is that n cannot equal -1. If it equals -1, you can't use this rule because then you're dividing by 0, which is undefined. And we've used this rule for algebraic functions, algebraic powers. So let's just review that first, and then we'll talk about how we use this rule with our non-algebraic functions as well. So for example, if you have a function to a power, what you can do is define your u, find the derivative of that, and then the differential. So when you're using this rule, you have to have the du factor there, and it has to be exact before you can plug into this formula. So we take a look here. Do we have the du factor? Yes, we do. It's exactly what we want it to be, so we can integrate. We can pull this 3 in front of the integral sign if we want. We can leave it there. It really doesn't matter. I'm going to plug into this formula. It's going to be 1 over n plus 1. Well, I've got the 3 there. Over n plus 1 times u to the n plus 1 plus c. So that 3 will cancel, and my result is this. And we can check by taking the derivative of this and seeing if it equals this. In this example, I had my du factor exact, but usually you won't have it exact, and you're going to have to play around with the coefficient. So let's take a look at this example. In this example, I'm defining u as 3x squared plus 2. That's the thing that's to the power of 4. So my du factor will be 6x dx. I look to see if I have that. The important part of that factor is the x. You can't bring an x in if there isn't one there. But you can bring a 6 in. You can multiply by 6 as long as you also divide by 6. That's allowed. So I'm going to multiply by 6, and then I'm going to divide by 6, and I'm going to do it outside the integral sign. I haven't changed the value. I can bring that 1 6 in, multiply by 6, and it's still a 1. But remember, the only thing you can play around with is the coefficient. You can't introduce an x and then bring a 1 over x outside the integral sign. It does not work. It's only coefficients. Now that you have your du factor exact, it's going to be 1/6 times 1 over n plus 1, so n plus 1 will be 5, times this function, my u to the n plus 5 plus c. Clean it up, and this is the integral. So we've done these kind of functions before, but now I want to use this formula with non-algebraic functions, which are called transcendental functions. And before we do that, we need to review the derivative of transcendental functions. So let's take a look. If you do not have these written out on a piece of paper for yourself, I highly recommend that you do that. You're going to want to refer to these rules as you're going through a number of different methods of integration, because you could be working with transcendental functions, and you have to be able to recognize what the derivatives of those transcendental functions are so that you can recognize whether you have the differential or not. I've got the 6 trig functions here, and then I've got the inverse trig functions here, inverse sine, inverse tan, and you don't have to worry about inverse cos so much because it's just the negative inverse of inverse sine. So I wouldn't even worry about that one at this point. focus on inverse sine u and inverse tan of u. Then we have the log and the exponential functions. Again, you probably don't need to worry about these two rules because when you get into doing integration, typically with log functions and with exponential functions, you're going to be working with base e. You might want to have those on there, but I suspect you'll rarely need to use them. Instead, focus on the derivative of natural log of u, which is 1 over u du dx, and the derivative of e to the u, which is e to the u du dx. If you have a base other than e, it's a similar derivative, but there's an extra factor in there. So let's take a look at some examples of using the general power rule when we have transcendental functions. So in our first example, remember that when you see cos to the 4th power of x, that's the same as cos of x to the 4th power. So this is our u to the nth power. So we express what u is in the margin, and I highly recommend that you do this. Define your u, find your du factor, and then do the integral. It takes a few more minutes to do this, but it will help you in the long run, especially as these functions get more and more complicated. When you write the u, do not include the exponent. I'm not putting u to the n, I'm just putting what u is, which is the base. So I do not include the power of 4. We can find the derivative of cos of x by looking at our formula sheet. So the derivative will be negative sine of x times the derivative of x, which is just a 1. Now we can express our du factor will be negative sine of x dx. We simply multiply both sides by dx. So this is our du factor. That's what we want to be here in order to use this rule. Notice you have to have your du factor and it has to be exact. So we look, it's close, we need a negative. So we're going to multiply by negative 1 here. Remember to include brackets when you multiply by negative 1 to show that it's multiplication and not subtraction. And then we're going to divide by negative 1, so we can do that outside the integral sign. Now that I have my du factor exact, I can plug into this rule. We have a negative here. 1 over n plus 1 will be 1 over 5. And then u to the n plus 1, so cos of x to the power of 5, which I can write with brackets and of power of 5, or I can also write it like that. And if it's indefinite integration, remember to add your constant of integration. Let's look at our next example. So we've got the integral of the natural log of x, the whole function to the power of 5, times 1 over x dx. So you're always hoping that whatever else is in there is part of the du factor. Again, we can write this as natural log of x to the power of 5, if that helps. And we can see that u to the n is this to the 5th power, so u is natural log of x. The derivative of that is 1 over x. Again, look at your formula sheet. So the du factor will be 1 over x dx. Do you have it? Yes, and it's exact. You do not have to do any manipulation. So now, again, we plug into our rule. So it'll be 1 over n, so 1 over 6. Natural log of x to the power of 6, which I can write like that, plus c, and we're done. Let's take a look at some more examples. In our next example, we can see that u to the n is here. So u is 2 plus 3e to the 2x. We take the derivative of that. Derivative of 2 is 0. The derivative of 3 times a function will be 3 times the derivative of that function. The derivative of e to the something is e to that something. Then times the derivative of that something, the derivative of 2x is 2. Then express the du factor as 6e to the 2x dx. And if you want to go straight from u to your du factor, that's fine. I just don't want to lose anybody, so I find the derivative, and then I just multiply both sides by dx. Do I have this du factor? Almost. I have the e to the 2x. I'm missing the 6, so I can introduce a 6 as long as I balance it. If I multiply by 6, I also have to divide by 6, and I can do that division outside of the integral sign. Now that you have it exact, we can plug into our formula. So it'll be 1/6 times 1 over n plus 1, so 1/5, times u to the n plus 1 plus c. and clean that up. And we're done. Let's take a look at the next example. Now, in this case, we've got 1 over something. We don't know how to integrate that, but we can write 1 over the square root of something as a power. So we can bring that out of the denominator. The square root is to the power of 1/2, and when we bring it out of the denominator, it becomes -1/2. So I can write that as natural log of x to the -1/2 dx over x, or I can split it up 1 over x dx. In this case, here's my u to the n. So u is natural log of x. du dx is 1 over x. So du is 1 over x dx. Now you can see that we do have the du factor. So now we're going to integrate using our general power rule, which says that the integral will be 1 over n plus 1. So -1/2 plus 1 is 1/2 times the function to the -1/2 plus 1 plus c. And we can write that as 2 times the square root of natural log of x plus c. Let's do a couple more. In this example, we do not have a power. When there's no power stated, we know the power is a 1. And because we have the integral of sine of 2x, and we know the derivative of sine of a function is cos of that function times the derivative of that function, let's let this be our u to the n. So we're going to think about it to the power of 1. So u will be sine of 2x. The derivative of sine of 2x is cos of 2x times 2. And so the differential will be 2 cos 2x dx. I like putting that 2 out front so that you're not tempted to multiply 2x times 2, and also so then we can get rid of the brackets. So do I have the du factor exact? Almost. We have the function part, but we're missing this coefficient, so I'm going to introduce a 2. I'm also going to divide by 2. Now that I have the du factor exact, I can integrate this. So it'll be 1/2 times 1 over n plus 1, which is another 1/2, times the sine of 2x to the power of 2 plus c. And I would clean that up and write it as 1/4 sine squared of 2x plus c. So sometimes the power is not going to be obvious because the power is a 1. Next example, we don't use e to the 2x as our power. What we're going to use is this, but we're going to bring it out of the denominator. So it will become e to the 2x plus 1, again to the power of -1/2. And let's define our u. This is our u to the n. So u is e to the 2x plus 1. The derivative of that is e to the 2x times 2. So the differential is 2e to the 2x dx. Do I have the du factor? Almost. I need a 2. So I'm going to multiply by 2 as long as I also multiply by 1/2. Now that I have the du factor exact, I can integrate. So it'll be 1/2 times 1 over 1/2 1/2 times 1 over 1/2 is the same as 1/2 times 2. And that simplifies to a 1. So there's my integral. So we're using this general power formula as long as I have the du factor and as long as that du factor is exact. So practice these on your own. Have your formulas handy so that you can refer to them easily, and recognize that when you have a product of things, probably one of those factors is part of your du factor. In the next video, I'm going to take a look at another pattern or method called basic log form. See you then.